Hi, everyone, and welcome to Intro to OOP. But before we have the Intro to OOP, I'm Olivia Lynn. I just wanted to break down some of our work sessions we have. I'll talk for an hour today, and then we'll have a work session after that. But don't worry if you aren't finished in time, because we will be spending Wednesday to continue the problems given today. We'll also have optional deep dives throughout that session on topics like UML, solid principles, composition versus inheritance, and more. And then on Thursday, we will take some time to dive into CI, documentation, best practices, and more. And you'll have time then to go back and polish what you've been working on in the previous work sessions. And before I launch into the talk, please feel free to ask any questions at any point while I'm talking. I'm always open to clarify anything I've said. And as a quick show of hands, who here has heard of object-oriented programming before? Wow, okay, fantastic. And has anyone used it in their own code before? Fantastic. Okay. So objects, just sort of get us loose and engaged. I'm going to count to 3, and when I do, I want everyone to look around them and out loud name 10 different objects. Anything, just name whatever you see. Ready? 1, 2, 3. Chair, desk, table. All right, great job, everybody. Now, pick one of your objects. Is it flat? Is it big? What color is it? Is it made out of anything? And beyond these descriptors, or one might say attributes, does your object have any functions? Can it hold other objects? Does it keep you warm? Can it contain information? Can it connect to the internet? And now that we're all thinking about objects, let's dive in. What is object-oriented programming? It's a programming paradigm that's based on objects. Some other popular paradigms you might have heard of are procedural and functional, and some popular languages that have object-oriented programming capabilities are Python, Java, C++, and C#. And there are many, many more, but these are the crowd favorites. And what is an object? It's an instantiation of a class, which is essentially blueprints for making objects. Sorry for the tautological definition, but an object has attributes and methods. And just a quick sidebar, the terminology can vary depending on what language you're using. This presentation is going to be focused on Python, so we'll stick with attribute and method. I know some of you here have experience with C++, so you might be used to slightly different wording. So now, let's say you picked a laptop as one of your objects. Think about the attributes. How heavy it is, how old it is would count, who it belongs to, and all of its specs like resolution, memory, all attributes, methods, turning on and off, displaying info, making noise, short-circuiting if you pour your water on it. And then beyond that, for the sake of example, I took some time to guess some other objects around us. These are written as class diagrams in UML, or unified modeling language, where the attributes are written on top and the methods below. And here we see an example, oh my gosh, the laser. Here we see an example of inheritance, where water bottle and coffee are both beverage-type objects. So they contain all of the attributes and the methods of beverage, but they add their own specific functionality. I apologize, I don't drink iced coffee, so it didn't occur to me. We can actually add ice to a coffee, so perhaps that should be up in beverage. UML can be really helpful for more complex code bases where you have a lot of stuff going on. Beyond just describing classes and relationships as we do here, we could use UML for things like sequence diagrams, deployment diagrams, and much more. And objects can also represent more abstract or conceptual entities, such as roles, responsibilities, or parts of a system's architecture. For example, we have managers, controllers, views, and services. We could imagine an email service. Well, an email object maybe could have a send self method. It's a lot easier conceptually to have a centralized class that will handle this kind of functionality. And when we go to extend this and build features, we know where to go for managing emails. And now let's take a look at refactoring a little spaghetti code that I wrote to demonstrate the benefits of object-oriented programming and walk through the 4 main pillars. I'm going to need to take a minute to rearrange the desktops. If you go, actually this is an old link, if you go to just the main session 21 repo, you can find the notebooks I'm using for this and follow along if you'd like, or you can just sit back and watch. Okay, so the pillars of OOP, they're principles that guide the design and implementation of object-oriented systems. And these will help you just make sure that your code is modular, reusable, and maintainable. And then this is a little thing that I need to run because I have a linter in my IDE, and it'll get very annoyed at the stuff I'm going to do. All right, so just to go over some of the basic terminology, if you want to go back and reference this, I included it at the top. We have attributes, methods, classes, objects, instantiation. A little fun thing is the constructor that gets called when we instantiate an object, and it sets up all of our object's attributes for us. And then self is a thing that you'll see in Python syntax for classes. So you'll just have to say like self dot our attribute for any class attribute you want to be accessing later. It lets us know that this is different than just a local scope variable. If you just aren't so familiar with this syntax, this is here for reference. And note, best practices include using Pascal case for the class name and then snake case everywhere else, which is just all lowercase and underscores. All right, so the starter code. This is just a sort of rough spaghetti example of making a smoothie as bare-boned as we can get. We have some concept of the blender, how big it'll be if it's plugged in, and then we just jump right into peeling a banana, adding it in, and then we go ahead, we wash and we de-leaf a strawberry, we add it in. We do realize at some point we might, make an over-full blender, so we just check. And then we go ahead, we add another strawberry in. We decide we're ready, we plug the blender in, and then we check that it's not too full to blend, and we go ahead and we make the smoothie. This is what we're going to be mocking up in object-oriented programming. So, and then we see the console output, and then we have the smoothie. So, let's start out by writing some scaffolding for the objects that we'll want to use. Let's see if I can to keep this big, but then let us still see enough of the starter code. I might actually have to make a tiny bit. Okay, so from our overview, and then looking through just these 2 columns best I can, what are some objects that people notice might be at play here? Yes, fruits, absolutely. And now you might have, you might be thinking a few steps ahead, in which case, I apologize, we're not going to use the class fruit yet, and we're going to just start out with the banana and the strawberry. We'll go ahead and we'll just do rough scaffolding for now. Oh, God. I am so not a fan of talking and typing at the same time. I don't know why. Okay. And then what else might be at play here? We do see towards the bottom of this, we're checking some things about an object. Does anyone know what object that might be? Yes. Yes, fantastic. Oh, God. Okay. I swear I sometimes do know how to spell things. All right, and we're going to take away the type annotations here, keep it simple. And then one sort of maybe less obvious object we're going to be using here is a smoothie, which will contain a lot of the, which will contain a lot of the concept of what we're holding here. Sorry, let me actually pull up the solutions. Oh my gosh, okay. I won't pull up the solutions, the internet isn't working. Okay, I'll pull them up. Here, my apologies, let me just undo this and, okay, see, oh my gosh, how do we go out of Zen mode? Okay, I won't pull them up. Okay, this is great. All right, so you'll see the solutions in the repo. Let's see if we go out of here, and then we just bring up, just to have on reference, just to check as we go along. Okay, great. Okay. So here is our scaffolding. I apologize, I haven't done a live demo in so long, and God, I'm not very good at typing. Okay, great. So here's the scaffolding that we can start with. It can be helpful to just throw down the objects that you're going to be working with. If you like writing doc strings at this point, that's also a very helpful time to just get a very high-level perspective of what classes you're using, what inheritance relationship they'll have, and what you want to be doing with this code. And now, let's start with pillar number 1, encapsulation. Encapsulation is the bundling of attributes and methods that operate on the data into a single unit, which is typically a class. It restricts direct access to some of the object's components, which can prevent accidental modification of data. And this essentially hides the eternal state of an object and requires all interaction to be performed through an object's method. And this is known as information hiding. The benefits of this include improved code maintainability, enhancing security, simplifying debugging, and just overall a better conceptual framework for this. So I started us off with actually all of the solutions. We'll just go with this because typing is not perhaps my favorite thing to do live. So here we have all of the kind of scattered variables we had at the top now bundled into our constructor for Blender. And then we go ahead and we add in this method, add to Blender. And note, you might be like, oh, well, hey, can't we just say blender.contents? Why can't we just append into that? Why do we need all of this? But one of the benefits of having a sort of setter method like this is we can include these checks first to see, is it even a valid operation to add this to this class attribute? Maybe we don't want to let the user affect the attribute in this way. Then we're going to go in, fill out the rest, plugging it in, and blending. Here we have the smoothie object that we're creating. And here we're keeping it pretty simple. We just initialize it with whatever contents we want in it. And we have repr, which is just going to give us a string representation of the smoothie itself. Then we can add in the next ones, which we'll just go ahead and we'll say, hey, here's this banana. We want just like the name. We want if it's peeled, and then we'll want to be able to peel it and also say, hey, this is in fact a banana. So then we can go ahead and we can do the same thing with the strawberry, noting instead of peel, we'll have these other extra methods. And then a note on access levels here. So Python's a little bit finicky about public and private. We can't even really get into protected with Python, but essentially private attributes and methods can or should only be accessed internally. And we can indicate privacy with leading underscores, but there's no way to truly enforce this in Python. The two ways of a single or a double leading underscore are very similar. If it's a single, it'll be a weak internal use indicator. This will be helpful for any kind of from module import star, although that is something you should try to avoid using. More on that on Thursday. But this will not import an object whose name starts with an underscore, and it's a good convention just to gently tell other programmers, hey, this thing is not intended for anything external. And if we use a double leading underscore, we will get a little bit of behind-the-scenes magic here, where the interpreter will change the name to prevent someone from accessing it in a more like traditional way. Here we have an example of just a very simple class. We could print this, and it would show us, but we would know as programmers, someone put this single underscore for a reason. We probably shouldn't be doing this. But if we go ahead and we try to print the second one, we won't be able to, because we won't be able to find that attribute. Technically, we could, so just know that for security reasons, this won't truly hide it. But these are really good conventions to follow for any time we want to make something private. And if we go back up to here, say we don't really trust the user with electricity. Like say, we don't want to let them deal with the plug. That maybe introduces us to liability. We could go ahead and say, like, hey, this attribute, we're not going to let them deal with this. And so this will prevent them from going in and saying, hey, Blender is plugged in equals true. And then we'll just have to go ahead and update that here and everywhere else. But it helps us to sort of gently nudge the user, tell them what they are and are not allowed to do, and have a little more control over who uses what in the code. Now, the second pillar, abstraction. This one involves creating simple models of complex real-world entities by focusing on the essential qualities rather than specific characteristics. This reduces complexity and allows efficient design and implementation by providing only the necessary details and hiding everything else. Yes?
I was just wondering, sorry, from above, I've always wondered why you have to call a variable with like self when initializing.
Oh.
Yeah, I wasn't sure about that.
Yeah, excellent question. Okay, so.
Yeah, in functions.
Yeah. But coming to here, I don't know if this is, so you're mostly asking about why it's self in here?
I feel like I understand
Okay.
that's necessary, but like why do you have to call it as, like, in the definition, basically?
In the definition?
Like in the arguments. Why is it
Okay.
intrinsic to something in class?
Okay, so if we say we wanted to do like a, we could do a sort of like special name, wow, I really, okay, variable. And say we wanted to be like Mr. Strawberry or something, then we could have this as like a local scoped variable, but then we wouldn't be able to access this from anywhere else. Like we wouldn't be able to say like return a special name, like that, like it just wouldn't be able to get to that. But then if we put that in self, then we know that that then becomes accessible from other places. So it helps us keep like any sort of local variables that we're using in the methods kind of clean and not like cluttering everything else. Does that answer your question? Okay. Yeah? Oh, okay. Okay. Any more questions on encapsulation? All right. So abstraction. So reducing complexity, just showing the necessary details. And now if we were to implement abstraction in here, we would go about doing that by like maybe saying, hey, we like really don't need all of like these strawberry things going on. Like all the user really needs to know All the user really needs to know is that like we're going to be preparing the strawberry. So we would just create a little method here in Strawberry that just grabs these two things that we would need to do to get it prepared. This makes it a lot simpler for the user to just approach it. They're like, okay, I don't need to know what's going on under the hood. This is just a black box. Instead, I'll just kind of, like I peel the banana, just prepare the strawberry, and now it's taken care of. Any questions on that? Cool. All right, inheritance. This is one of my favorite ones. It allows a class to inherit attributes and methods from another class, which promotes code reuse and creates a sort of natural hierarchy between the classes. So if you hear about parent classes or subclasses, that's inheritance. It promotes reusability, code maintenance, natural hierarchy. And then how we would implement this is as the fruit class, as suggested before, we could just go ahead and create this, this fruit class that has the concept of being peeled, washed, and de-leafed, and then also bundles in this representation that we've been using in banana and strawberry. And then banana and strawberry could both inherit from the fruit class by using this kind of syntax, throwing the fruit in there, and then some notes on how we grab some of the concepts from the parent class. We can just go ahead and say like the super init. If we then wanted to go do any other code, we could just throw that below, just using this super parenthesis syntax. And then if we are inheriting from a parent class, we can still have our own methods on top. So we have a de-leaf method still in strawberry, but we decided that all fruits can be washed. So we're going to bring this wash method up to the fruits. We could wash a banana. It would be weird. We can do it. So we'll give this to fruit. Now all fruits can be washed. And so we still have to call that in strawberry in our prepare. So we'll go ahead and we'll wash it, but de-leafing doesn't make sense for banana. So we'll keep that in strawberry. And so now we have some of the functionality shared between all fruit classes, but we still have some specific methods to each class to justify the class still being there and being defined, but create a sense of cohesion, hierarchy, and to just keep things from being redundant. Any questions on that? Yes, wow. Oh, okay, yes, fantastic. Okay, so super is basically, so we see this fruit.wash. I think I'm a little bit shaky on older notation, but you could just do something like fruit. It's essentially, we are basically copy pasting the wash here. Everything in there gets called first from the super. It sort of is like if we, okay, I'm sorry, I'm not doing the best way of describing this. So it was before self-wash, and now instead it just points to where that method is defined in the super class. Does that? Yes, that's precisely it. I think it could just be fruit. I always use super. I think I've seen something like this. I would Google to be sure, but it's just grabbing what you've inherited from there. Any other questions?
If you did self.wash there, would give you an error?
Yes, because that is no longer. Or wait, oh my gosh, actually, maybe it wouldn't. Actually, I don't think. No, I think it would. Let's find out. No, it would not, because it already inherited it from above. Why do we do super? Because if you wanted to, if you were extending the wash method from your super class into, say, when we wash the strawberry, we want to make this a little bit special. So we could go ahead and do this super.wash, but then we could do something else here, and then it would just grab everything from the wash method in the superclass, but still let us do what we wanted down here. But because we've defined the wash method in Strawberry, our self.wash would then be pointing to that. So it's just good practice to just call super. Yeah, no, you're right, but we could just do self-wash. Thanks, good eye there. Yes? I'm so sorry.
Sorry, is there a reason you give the base class, the root class, when Banana's can't be dealing with it all? Why not just give the Strawberry?
I did that for convenience and because I'm lazy, but it could be in Strawberry. I think the way I have this playing out is that we kind of think it's just slightly, oh no, oh my gosh, it's because I made a typo. Later on, we just keep is deleafed in the Strawberry, and we have a concept of is prepared. You're right, deleafed should be specific to the Strawberry, but if we're never going to access it from Banana, we won't run into problems, but it should just be in Strawberry. Any other questions? Okay. All right, so polymorphism. This one is our last pillar, and this one is maybe one of the most special aspects of object-oriented programming. This one allows objects of different classes to be treated as objects of a common superclass. And in Python, it's typically implemented via method overriding, where a subclass provides a specific implementation of a method that is already defined in its superclass. And its main purpose is to allow one interface to be used for a general class of actions, making it easier to write code that works on a general type rather than a specific instance. And this makes our code more flexible and extensible. We can add classes with minimal changes. We can simplify our code, and we overall do improve our code readability by using polymorphism. This is part of why maybe the fruits is a little awkward in the state it's in, because we are building up to this final example of our fruits class, where we have a now abstract, not implemented method called prepare. We decided, hey, in the banana and in the strawberry, in the banana we're peeling the banana to prepare it, and in the strawberry we're doing these other things to prepare it. Aren't we just preparing both of the fruits? That should be a concept in fruit. So we go ahead and we create this, but we know that the implementation will be different based on the subclass. So we create this as an abstract method with a little note that we shouldn't ever be calling fruit.prepare. And then we go in the banana and we implement the prepare method. We know this is pretty simple. We'll just be doing self.peel, and then we'll be able to set it to is prepared. This is prepared was established in the fruits constructor. So we get it in the banana. And then in the strawberry, we already had our prepare method, so it can look the same. And then we set it to is prepared. And what's great about that is that, like, okay, so if we go up before, in the previous iteration, we were having to still declare each object and then perform things on it like this. But now that all of our fruit objects have this same common interface with polymorphism, we can just treat them all the same way. We can say, hey, just take the ingredient, just prepare it, and then we just add it in our blender. And then we go ahead and we blend the contents. And it works as expected. And so polymorphism is a little bit more, it goes beyond that a little bit more in other languages. You'll run into concepts of method and operator overloading. That generally you have to cheese in Python. Essentially, method overloading will be defining a method that can take different types of inputs, and then based on what inputs you call it with, whether it's like a single integer or maybe it takes in 2 floats, it will access just different behaviors that you've defined. In Python, essentially, you're just going to be using that kind of behavior by defining keywords, and you might not even realize that that's what you're doing, that that's a kind of polymorphism. So we're just going to focus on this as Python polymorphism. Any questions on polymorphism? Okay. So now that we've gone over encapsulation, abstraction, inheritance, and polymorphism as the 4 pillars of object-oriented programming, we can get into some really fun things that happen when we combine these concepts. For example, abstract-based classes are very convenient tools that provide a way to define abstract methods that must be implemented by any subclass. They're used to define a common interface for a group of related classes, and an abstract-based class cannot be instantiated on its own, and it solely serves as a blueprint for other classes. And here's a very quick example of how we would implement and use it. So we have to do this import. If we just make this and we basically create this abstract method just like we did in Fruit, and then each of these have their own separate implementations, and we get our outputs. This is, oh, yes?
Sorry, I just
No.
back to the self thing.
Yes.
Sorry to hold up on it, but I'm just, why would you put that in the argument if you don't need to call it in the function? Is that just like what is typical to do, or do you? I just don't quite understand what's going on.
It's certainly something I just don't think about anymore. I just always do. So does anyone here have an answer that, yes.
Yeah, so by default, Python classes will always feed itself as a first argument to any method, unless you decorate the method with a static class or static method or class method, then it'll feed a class instance. So it's always good to have self there even if you're not planning to use it, unless you explicitly state it's a static method.
Yes.
I just want to say, too, that self is just a convention. You can really call it anything that you want in Python. You can call it this if you wanted to.
Okay. Oh, word. Cool. Wow, I'm learning. Cool. Any other questions or comments? All right. And then we also have an idea of mixed-in classes, which use inheritance and encapsulation. And this extends on the syntax we saw above, where we can essentially form multiple inheritance, where class can inherit attributes and methods from multiple parent classes, which gives us shared functionality and reusable components. So if we were to add in this little logger mix-in, we would be able to grab this method from within this mix-in class and be able to create a dog that has its bark be logged. And then some final remarks. So just a summary of what we've gone over, objects, classes, all the different pillars, and a little quick aside on the criticisms of object-oriented programming. It's important to know just because you're holding a hammer doesn't mean everything's a nail. And keeping these in mind can help you to code better when you are coding in object-oriented programming. Sometimes people say the focus on objects means you won't think so much about algorithms and functional aspects of what you're doing. Also, it can take a little while to code in object-oriented programming and to compile. The learning curve can be steeper. There can be some overhead, and then sometimes you do end up with code bases that have very complex, tightly coupled class hierarchies. However, just because there are some criticisms does not mean there are not any benefits. In general, object-oriented code will be far more modular because we have our objects being self-contained. It's easier to debug them and to collaborate with other people, knowing that, hey, all the functionality in this object is going to be in this object's code, all encapsulated. So while Drew is working on that, I can easily work on the data manager, and we'll be able to submit our pull requests and not deal with any sort of conflicts. Reusability also, it's very, very convenient to just be able to inherit from a class, know that everything that was in the first one is going to be there in the second. You don't have to rewrite code, and you don't end up with divergent changes, which can be a real headache. It's scalable, it's flexible, it's maintainable, and it does create a natural mapping to real-world entities, which can be very conceptually helpful. Any questions? All right, so now that we've gone through and we have a smoothie and perhaps a working understanding of the principles of object-oriented programming, I'd like to invite everybody to go to the repo and check out the OOP exercise Python notebook, where we're going to be using object-oriented programming to create a flashcard study tool. Thank you all. That's a good point. I just want to clarify also, the example was sort of an example of how it can be easier to think in object-oriented programming rather than procedural for these sorts of things. I don't recommend starting with spaghetti code and refactoring. Certainly the UML that I showed in the beginning is kind of how I would try to approach designing an object-oriented solution to something, mapping out the classes and how they interact and what attributes methods you might want. But sometimes we do find ourselves coding at 3 in the morning. We're exhausted. We just need to get some stuff in. So sometimes you might have to refactor things into objects, but definitely recommend starting with the high-level plan.